Hello there. And in this video we're going to introduce an application of integrals. And this is sometimes referred to as solids of revolution. So let us begin by first considering a function, and let us assume it's f of x is equal to negative x plus 1. So we know what that curve should look like. That is just a line that has a negative slope, goes downward, and a y-intercept of 1. So this is f of x. So let's assume that this is the x-axis and the y-axis. And let's consider the area bounded by f of x, the x-axis, and the y-axis. So the x-axis, of course, is the horizontal, vertical axis is the y-axis, so the area bounded by these three functions is going to be equal to this region here. And we're going to consider revolving that area about the x-axis. So what do I mean by revolve? So you can imagine, let us look at the mirror image of this line here. So the mirror image of this line is going to be here, so that's going to be negative f of x. So the mirror image of that area is going to be here. So if we sort of flip this upside down, then that area is going to be superimposed in this region here. And if we revolve it around the x-axis, then that means we're going to have a bunch of circles that is going to pretty much look like this region. So if you sort of look at this from another angle, the base of this is going to be the longest side, and then this is going to sort of narrow out to a point. So for example, this circle here could be like a point in the middle. This circle here is generated by this point here, and this tip point here is located right there. So this axis here is precisely the x-axis, and this is the y-axis, and then pretty much what we're looking at here is the z-axis. Alright, so a couple questions that we can ask ourselves is the following. The first question is, what is the volume? So what, it's an ugly W, so what is the volume of the generated solid? And the second question would be is, what is the surface area of the generated solid? So this can pretty much be applied to, you know, some basic engineering problems or some architectural design type of applications. All right, so how can we answer these two questions with calculus? So let's answer the first one. What is the volume of this surface? So let us look at this solid again. So if we revolve it, it's pretty much a cone, right? A right circular cone. So the radius originally, when we begin, and let's look at it from this angle as well. So this is the x-axis, and let's assume that's the x-axis. So these pink points represent the same exact point. So what is the length of the base? So that means what is the length of this region? So if this curve is y is equal to negative x plus 1, well, when x is equal to 0, this value is equal to 1 because this is the point 0, 1. And by symmetry, this is going to be the point 0, negative 1. So this point located here, and it depends on the perspective you look at this, we can call this 0.1, and we can call this point 0, negative 1. Right? So that means this is the positive y-axis, but it doesn't really matter the orientation. But nonetheless, the radius of this circle is going to be 1. So let's pick another circle a little bit farther up. So let's look at this radius here. So let's color this blue. So this circle, and namely this radius here, is going to be that height. So if I pick a point, say x, what is that height going to be? Well, that height here, this radius, is going to be equal to whatever height value that function has at that x point. So that's going to be equal to negative x plus 1 in general. And that's going to be applied to pretty much any line segment you choose along this trajectory. Okay, so we have a bunch of circles and we know all their radiuses. So if we add up all of the areas in this entire cylinder, because that's pretty much what volume is, we're pretty much just stacking areas on top of each other, then eventually if you accumulate all those infinite areas, or an infinite number of areas, then you're going to get the volume. And this is a very important concept. So the volume is pretty much the sum of areas. And it's almost like an infinite sum, actually, since it's pretty much a continuous space that we're filling up. So the volume is equal to an infinite sum of areas. And remember that integrals are also an infinite sum as well, because it's the limit of a Riemann sum. All right, so let's see if we can formulate this in terms of integrals. All right, so here's our solid that we are revolving. Let's look at a cross section here. So this radius is equal to the height of the function at the point chosen. And let's assume that point is x. Right? So let's call this point A, and let's call this, so this is x is equal to A and x is equal to B. We'll find x is equal to B in a moment. So if we find the area of this green circle, the area of that circle is going to be pi r of x, the quantity squared. And what we want to do is add up all of those areas from x is equal to A all the way up to x is equal to B. So that means the volume is going to be equal to the integral from A to B of pi r squared with respect to the x-axis. And based on this picture, r is f of x. So this is pi r squared. And some people refer to this as the shell method. Okay, so let's figure out exactly what f of x, a, and b are in this picture. So here's our curve again. So this is f of x is equal to negative x plus 1. So I want to know what this point is, and I'm defining this point here to be equal to x is equal to 0. So this is the x-intercept. So the x-intercept is located when y is equal to 0. So when y is equal to 0, negative x plus 1 is going to be equal to 0, so x is going to have to be equal to 1. So that means we need to integrate from x is equal to 0 to x is equal to 1, where f of x is negative x plus 1. So that means the volume is going to be equal to the integral from 0 to 1 of pi times negative x plus 1, the quantity squared, dx. And we can figure out this interval via the fundamental theorem of calculus. So that means the volume is going to be equal to the integral from 0 to 1 of pi times, let's FOIL this out. So we have x squared minus 2x plus 1, the quantity, times dx. And we can factor out this pi if we want to. So v is equal to pi times the antiderivative of 0 to 1 of x squared minus 2x plus 1 dx. So let's integrate. So the antiderivative of x squared minus 2x plus 1 is going to be equal to 1/3 x cubed minus x squared plus x. And we need to evaluate this as x goes to 1, x goes to 0, and subtract. So when we plug in 0, everything is 0, so nothing special happens there. So when we plug in 1, we're going to get 1/3 minus 1 plus 1. 1's cancel, so we just get that this is equal to pi over 3. So that means the volume is equal to pi over 3 cubic units, whatever the unit is that we're pretty much looking at. So now let's answer the second question, the surface area. Let's consider the same exact solid again. So here is our cross sections. So what we want to know is the surface area of this object. So we're going to be calculating all of these pink lengths here. So what do we have? So if we look at this, from here to here is just a bunch of circumferences of circles. So that will be the surface area of this and all of its boundaries. But also remember that we have this base that also has some area associated to it as well. Because yes, we can calculate the surface area of the outside, but also the base has some surface area as well. So it has some circumference of circles, and we also have this pi r squared sitting at the bottom, where the radius of that is the maximal value of f. So how can we generate that? So that means the surface area is going to be equal to the area of outside plus the area of base. So the area of the outside part is going to be equal to the integral from 0 to 1. So how do you find the circumference of a circle? So that's going to be 2 pi r. So 2 pi, and the radius of each of these circles is still dictated by f of x. So f of x is negative x plus 1 dx, plus the area of this circle on the outside. So that's a fixed circle, so no integrals are needed there. So the radius of that circle is going to be 1. So that means the area of that circle is going to be pi times 1, the quantity squared. So this is the base area. A lot of people forget that part. So that means the surface area of the solid is going to be equal to 2 pi times the integral from 0 to 1 of negative x plus 1 dx plus pi. And then we can use the fundamental theorem of calculus on this. So we have 2 pi times, so the antiderivative of that is going to be negative 1/2 x squared plus x. And we need to evaluate this from 1 to 0 and subtract. So 0 sends the whole entire thing to 0, so nothing interesting there. So we have 2 pi times, so we plug in 1, so we're going to have negative 1/2 plus 1. 0 doesn't contribute anything. So 1 minus 1/2 is going to be a half, and a half times 2 is just going to be 1. So we have pi plus pi, which is equal to 2 pi. So that means the surface area of the object is equal to 2 pi square units. Because remember, volume is a three-dimensional measurement, and surface area, or area in general, is a two-dimensional measurement. And that is how you can use the shell method for determining the volume and the surface area of surfaces of revolution, or solids of revolution.